Top 25 Microservices Interview Questions and Answers. Microservices architecture has become a pivotal approach in software development, enabling teams to build scalable and resilient applications. This video presents a curated list of the top 25 interview questions and answers related to microservices. Whether you are preparing for a job interview or looking to enhance your knowledge, these questions will help you understand key concepts and principles. Get ready to strengthen your grasp on microservices and improve your interview performance. 1. What are microservices, and how do they differ from monolithic architecture? Microservices are an architectural style that structures an application as a collection of small, independent services. Each service is focused on a specific business function and can be developed, deployed, and scaled independently. In contrast, monolithic architecture combines all components of an application into a single unit, making it difficult to scale and update specific parts. Microservices enable flexibility, allowing different teams to work on various services using different technologies, while monolithic systems typically require coordination across the entire application for changes. This distinction leads to increased agility in development and deployment processes. 2. Explain the advantages and disadvantages of using microservices. Microservices offer several advantages, including improved scalability, as individual services can be scaled independently based on demand. They also enhance flexibility, allowing teams to use different technologies and programming languages suited for specific tasks. Furthermore, microservices promote faster deployment cycles, enabling agile development practices. However, there are challenges as well. Increased complexity can arise from managing multiple services, leading to difficulties in communication and orchestration. Debugging can become more complicated, as tracing issues across numerous services is not straightforward. Finally, the need for robust monitoring and security measures can add to operational overhead. 3. What is an API gateway, and what role does it play in microservices architecture? An API gateway acts as a single entry point for client requests in a microservices architecture. It manages and routes requests to appropriate microservices, facilitating communication between clients and backend services. The gateway handles cross-cutting concerns such as authentication, rate limiting, load balancing, and caching. By centralizing these responsibilities, the API gateway reduces complexity for clients, simplifies service discovery, and improves security. This architecture enables better control over traffic, enhances performance, and offers a unified interface for clients interacting with multiple microservices. 4. How do microservices communicate with each other? Microservices communicate through various methods, primarily using lightweight protocols. The most common approach is HTTP, RESTful APIs, which allow services to send and receive requests over the web. Another popular method involves using messaging queues or brokers, such as RabbitMQ or Kafka, enabling asynchronous communication. This allows services to publish messages that other services can subscribe to. gRPC is also gaining traction for its efficiency in inter-service communication. Choosing the right communication method depends on the use case, such as the need for synchronous versus asynchronous communication and the desired latency. 5. What is service discovery, and why is it important? Service discovery is a mechanism that enables microservices to find and communicate with each other dynamically, without hardcoding service locations. It is crucial because, in a microservices architecture, services may frequently change due to scaling, updating, or redeploying. Service discovery can be client-side or server-side. Client-side discovery relies on the service consumer to query a registry for service instances, while server-side discovery allows a load balancer or API gateway to perform this task. This process enhances resilience, reduces downtime, and simplifies the management of service endpoints. 6. Can you explain the concept of eventual consistency in microservices? Eventual consistency is a key concept in distributed systems like microservices, where data is not instantly consistent across all services. Instead, changes made in one service will eventually propagate to others, achieving consistency over time. This approach allows for higher availability and scalability, as services can operate independently without waiting for immediate updates. Eventual consistency often relies on asynchronous communication methods and can be managed through techniques like conflict resolution, where systems reconcile differing states when they converge, ensuring data integrity while maintaining performance. 7. How do you handle data consistency across multiple microservices? Data consistency across multiple microservices can be achieved through various approaches. One common method is using eventual consistency, where services update their data asynchronously. Techniques like the saga pattern help manage distributed transactions, allowing services to coordinate changes effectively. Another approach involves using a shared database, though this can lead to tighter coupling. Event sourcing can also be utilized, where changes are captured as events, enabling systems to reconstruct state. Ultimately, the choice of strategy depends on business requirements and tolerance for inconsistencies. 8. What is the circuit breaker pattern, and how does it help in microservices? The circuit breaker pattern is a resilience design pattern that helps prevent a system from repeatedly trying to execute an operation that is likely to fail. In microservices, it monitors requests to a service and can transition between three states: closed, open, and half open. When failures exceed a predefined threshold, the circuit breaker opens, blocking further requests for a set duration. This allows the failing service time to recover. Once in the half-open state, it gradually allows a limited number of requests to test if the service is back online. This pattern improves system stability and reduces cascading failures. 9. How would you implement logging and monitoring in a microservices environment? Implementing logging and monitoring in a microservices environment involves several key practices. First, centralized logging is essential. Tools like ElkStack, Elasticsearch, Logstash, Kibana, or Fluentd can aggregate logs from all services into a single location. Each microservice should log relevant information, including request IDs for traceability. For monitoring, use tools like Prometheus or Grafana to track service health and performance metrics. Establish alerts for anomalies or failures. Distributed tracing tools like Jaeger or Zipkin help visualize request flows across services, enabling easier debugging and performance analysis. 10. How do you manage versioning of microservices APIs? Versioning of microservices APIs can be managed through several strategies. One common method is URL versioning, where the version number is included in the URL path. For example, API v1 resource. Another approach involves header versioning, where clients specify the desired version in request headers. Semantic versioning can also be used, allowing developers to indicate breaking changes or backward compatibility through version numbers. Additionally, deprecation policies should be established to guide clients on transitioning between versions, ensuring smooth upgrades while maintaining service reliability. 11. Describe the role of containers in microservices deployment. Containers play a crucial role in microservices deployment by providing a lightweight, consistent environment for each service. They encapsulate the application code, libraries, and dependencies, ensuring that microservices can run reliably across different computing environments. This isolation simplifies scaling, as containers can be easily spun up or down based on demand. Containers also facilitate continuous integration and continuous deployment, CI/CD, practices, enabling teams to automate testing and deployment. Tools like Docker and Kubernetes enhance orchestration, management, and scaling of containerized microservices, promoting efficient resource utilization. 12. What are some common microservices design patterns, such as Saga or CQRS? Common microservices design patterns include the Saga pattern and command query responsibility segregation, CQRS. The Saga pattern manages distributed transactions by breaking them into smaller, manageable steps, ensuring that if one step fails, previous steps can be compensated. It allows long-running transactions to be handled gracefully. CQRS separates read and write operations, enabling optimized data models for each. This separation can lead to improved performance and scalability, as different data stores can be used for reads and writes, tailored to specific use cases. 13. How do you ensure security in a microservices architecture? Implementing security in a microservices architecture involves several strategies. First, use API gateways to centralize authentication and authorization, ensuring that only authenticated requests reach individual services. Employ OAuth 2.0 or JWT for token-based authentication. Next, secure communication between services with mutual TLS, MTLS, to encrypt data in transit. Additionally, regularly perform vulnerability assessments and implement logging for monitoring suspicious activities. Lastly, adhere to the principle of least privilege by restricting access rights for each microservice, reducing potential attack surfaces. 14. Explain the difference between orchestration and choreography in microservices. Orchestration refers to a centralized approach where a single service, known as the orchestrator, directs the interactions between various microservices. This service manages the flow and state of transactions, ensuring that each service performs its task in the correct order. In contrast, choreography is a decentralized approach where each service independently determines when to act based on events. Services communicate through events, enabling them to react to changes without a central controller. Both methods have their advantages, with orchestration providing more control and choreography offering greater flexibility and resilience. 15. How do you implement a CI/CD pipeline for microservices? Implementing a CI/CD pipeline for microservices involves several key steps. First, each microservice should have its own repository and build process to ensure modularity. Use tools like Jenkins, GitLab CI, or Circle CI for continuous integration, automating code testing and build processes. Containerization with Docker is essential for consistent environments across stages. For continuous deployment, utilize Kubernetes or similar orchestration tools to manage deployments efficiently. Ensure automated testing at every stage to validate functionality, security, and performance. Monitoring tools should be integrated to track the health of services post-deployment. 16. What strategies do you use for scaling microservices? Scaling microservices can be achieved through various strategies. One effective approach is horizontal scaling, which involves adding more instances of a service to handle increased load. Container orchestration tools like Kubernetes can automate this process, allowing for dynamic scaling based on traffic patterns. Another strategy is to implement load balancing to distribute incoming requests evenly across instances. Additionally, utilizing caching mechanisms can reduce the load on services by storing frequently accessed data. Decoupling services and using asynchronous communication can also help scale individual components independently based on demand. 17. How do you implement fault tolerance and resilience in microservices? Implementing fault tolerance and resilience in microservices involves several strategies. First, use the circuit breaker pattern to prevent cascading failures by stopping requests to a failing service. Implement retries with exponential backoff for transient errors. Employ bulkheads to isolate services, ensuring that if one fails, others remain operational. Implement health checks and monitoring to detect failures proactively. Additionally, leverage timeouts for external service calls and maintain redundancy, such as multiple instances of services, to handle failover gracefully. These techniques collectively enhance system reliability. 18. What is the role of a message broker, and how is it used in microservices? A message broker acts as an intermediary for messaging between microservices. It facilitates communication by sending messages between services, ensuring that they remain decoupled. This decoupling allows services to operate independently, enabling scalability and fault tolerance. Message brokers support various messaging patterns, including publish, subscribe, and point-to-point. They help manage message queues, ensuring messages are delivered even if the receiving service is temporarily unavailable. Examples of popular message brokers include RabbitMQ, Apache Kafka, and ActiveMQ, which enhance reliability and performance in distributed systems. 19. How do you handle configuration management in microservices? Configuration management in microservices involves managing settings and parameters for each service independently. Common approaches include using environment variables, configuration files, or centralized configuration management tools like Consul, Spring Cloud Config, or Kubernetes config maps. Services can dynamically pull configurations at runtime, allowing for easy updates without redeploying. It's essential to ensure that sensitive information, such as API keys or database credentials, is securely managed, often leveraging secrets management tools to avoid exposure in code repositories. 20. What considerations are there for testing microservices? Testing microservices requires a multifaceted approach due to their distributed nature. Key considerations include unit testing individual services to ensure their specific functionality, integration testing to verify interactions between services, and end-to-end testing for the entire system's behavior. Additionally, contract testing is crucial to ensure that services adhere to agreed interfaces. Performance and load testing help assess how services behave under stress. Automated testing should be implemented as part of the CI/CD pipeline to facilitate quick feedback and maintain the quality of the microservices ecosystem. 21. How do microservices handle deployment complexity? Microservices manage deployment complexity by leveraging automation tools and practices. Containerization technologies like Docker encapsulate each service with its dependencies, simplifying deployment across different environments. Continuous integration and continuous deployment (CI/CD) pipelines automate testing and deployment, ensuring that changes can be released rapidly and reliably. Service orchestration platforms, such as Kubernetes, manage service scaling and health, facilitating seamless deployments and rollbacks. This modular architecture allows teams to deploy services independently, reducing the risk associated with complex deployments. 22. What is the database per service pattern? The database per service pattern involves assigning a separate database for each microservice in an architecture. This approach allows microservices to manage their own data with autonomy, reducing dependencies on a single database schema. Each service can optimize its database according to its specific needs, which promotes scalability and flexibility. However, this pattern can introduce challenges in data consistency and requires careful consideration for inter-service communication. Implementing event-driven architectures can help synchronize data across services without tightly coupling them. 23. How do you implement inter-service security and authentication? Implementing inter-service security and authentication involves several steps. First, use token-based authentication, such as JSON Web Tokens, JWT, to ensure that each service can verify the identity of requests. Next, establish a secure communication channel using Transport Layer Security, TLS, to encrypt data in transit. Additionally, consider implementing an API gateway that acts as a single entry point, managing authentication and authorization before requests reach individual services. Role-based access control, RBAC, should also be utilized to ensure that services have the minimum permissions necessary for their functions. Regularly auditing and updating security measures is essential for maintaining a robust security posture. 24. What is the bulkhead pattern, and how does it apply to microservices? The bulkhead pattern is a design concept that enhances system resilience by isolating different components or services within an application. In microservices architecture, this means dividing services into separate pools or bulkheads, allowing them to operate independently. If one service fails or experiences issues, others remain unaffected, preventing a cascading failure across the system. Implementing bulkheads can involve using separate databases, queues, or even server instances for critical services, ensuring that resources are allocated efficiently while maintaining a level of fault tolerance. This pattern is essential for managing resource contention and improving system reliability. 25. How do you approach performance optimization in a microservices architecture? Performance optimization in a microservices architecture requires a multifaceted strategy. First, identify performance bottlenecks through monitoring and profiling tools. Next, optimize each microservice by analyzing its resource usage, reducing unnecessary computations, and ensuring efficient data access patterns. Implement caching to reduce latency for frequently accessed data. Utilize load balancing techniques to distribute traffic evenly across services. Employ asynchronous communication when appropriate to enhance responsiveness. Finally, regularly review and refactor services to maintain performance standards and adapt to evolving requirements. As you prepare for your microservices interviews, having a solid grasp of these 25 key questions can significantly enhance your confidence and performance. Understanding the principles and best practices of microservices architecture will not only help you ace your interviews but also set you up for success in your future projects. We hope you found this content valuable and informative. If you enjoyed the video, please give it a thumbs up and consider subscribing for more insightful content. Thank you for watching.